Now, let us consider a very large water resources system. So this is a water resources system. You have a river flowing through a catchment. This is the catchment boundary, which is also called a watershed. So, a watershed is basically the entire area which has a common outlet, namely this particular point here. This is the outlet of the watershed. And you may have the main river and its tributaries and its branches and so on. So let's say a civil engineer decides to create or build a dam along the river. Somewhere here we want to create our dam. What can be the reasons we want to build our dam? I might want to store the water for use in the non-rainy seasons and particularly for irrigation. So either I can use this water for irrigation water supply, or I can use it for industrial water supply. We may also, if particularly the terrain supports us, we may want to use the force of water, basically the potential energy, convert them to mechanical energy, and then so that mechanical potential energy can then be used to drive a turbine, and the turbine can be connected to a generator to be converted to electrical energy. So we can also build a dam for the purpose of generation of hydroelectric power. We also know that if, let's say, there was no dam here, these areas along the downstream used to get very frequently flooded, and somehow it so happened that there are industries or cities which developed along the course of the river, and we want to protect the cities from getting flooded every year. So we may want to build this dam for the purpose of flood control. So that's another application of dams. All right. And how this flood control is typically achieved is the water gets stored in the reservoir that is created behind the dam, and then it is regulated or controlled. The release is controlled, and the control release comes through something called a spillway. All right. Now, when we as civil engineers study about dams and water resources systems, our perspective is a little bit different. I know there can be some social scientists who question how sustainable these infrastructure such as particularly dams are, and they claim that it's not good or sustainable. I would like to mention here that although I'm not really capable of teaching you what sustainability is and whether or not a particular dam will be sustainable for the area is is up for an environmental assessment, but due consideration should be given to ecological sustainability in the river. For example, the river may be carrying some indigenous fish species, so due consideration has to be given to the ecological and environmental sustainability both upstream and downstream of the dam when we create the dam in the first place. And also, believably, hydroelectric power is more green, quote unquote green, as compared to fossil fuel burning. We know that fossil fuel burning contributes to greenhouse gas related warming of the atmosphere, and as a result a lot of changes in the whole climate system. So hydroelectric power do not emit CO2, so therefore they are believably more green as compared to fossil fuel burning. Anyway, leaving these aspects aside, let us focus from a civil engineering perspective. uh, so let's say I decide to build a dam. The very first question that would be asked is, once you build a dam and a reservoir that gets created behind the dam, how much of the area is going to be flooded? All the area that you see in blue here. This could have been somebody's home. So once you create a dam, you build a reservoir, and the people who are staying in that area would all be so that a whole area would be inhabitable. So the first question that you may want to ask is, how much upstream area would be flooded, or inundated because of the creation of the dam. And then in the upstream of the dam or in the downstream of the dam, how is the depth of water going to change? What volume of water should the reservoir retain? All these are questions which we will be addressing, partly at least, if not fully, in our discussions related to open channel flow when we come to that as part of this course. Now, here, of course, I told you that irrigation or even industrial water supply can be a principal reason for building a reservoir or a dam along the course of the river, and this is particularly important for India because our economy is agriculture driven. The day the India Meteorological Department proposes forecasts a normal monsoon year, our stock prices, our indices go up because ours is a very heavily agriculture dependent economy. So we realize the importance of irrigation water supply, and what is typically done is there are structures created in the reservoir that gets formed, which are called intake structures, and these intake structures, they supply either irrigation water or they can supply to municipal systems. For example, the city of Mumbai gets its water, well, actually from 7 reservoirs, not one, and they're very far away. None of them are in Mumbai. There are 7 reservoirs, some of them are as far as 125 kilometers away from Bombay. And there's a complex network, supply network, which is water supply network, that is laid to make sure that you and I, when we open the taps in our kitchens and the toilets, there is treated potable water coming at our disposal. So here, you know, then the question lies that if you have a network like that, you have a big reservoir and then you have pipes and then you have junctions, then you have valves, and eventually it reaches the end user somewhere. So then there are questions such as, where would I locate my storage reservoirs? I don't know if you have noticed, but in IIT there is one big huge storage reservoir near Samir. So there, where should the reservoir be located? Where should the main reservoir be, the master balancing reservoir? Where should the smaller ones be? What should be the diameters of these pipes? And what should be the velocity, the discharges in these pipes? Do I need to install any more pumps additionally? Sometimes what happens is, see, ideally, if you have a tank which is very, very high, we know from our 6th, 7th standard physics that water finds its own level. So if you have a water tank which is very high, you can automatically expect the water to come to your kitchen and toilet because your kitchen and toilet are lower in height as compared to the water tank. But rarely that happens because of demand and because of the fact that energy or head of water is lost when the water travels in these pipes, right? So do I need to install any more additional pumps? Where should I locate them? What how can I determine the head loss such that I know that the water reaches the target that it's meant to reach? So all of these concepts we will discuss in the module where we learn about flow through pipes. So all of this gets into our chapter on pipe flow through pipes. And these sort of flood control measures and all of that, depth of water upstream, downstream, all that we are going to learn in open channel flows. These are just different chapters and modules. All right. So now let's say, and municipal water supply, I have some sort of touched. What about irrigation water supply? We all know that there are canals. Particularly if you are aware of the green revolution that happened in India in states like Punjab, big irrigation canals were constructed. They were meant to supply water for irrigation. Now the question is, what should the material of the canal be? what should be the size of the canal, the width, the length, the breadth, the height, such that the irrigation demands are satisfied. And we all know that our designs should be efficient, quote unquote. Let's not formally define what it means. We are going to define it when we reach the bridge. Okay. So we know that our system, or we expect that our systems would be efficient. And as a channel, as you construct a channel, or as you use a natural channel, there can be constrictions or expansions, or humps and obstructions. So all of that, kind of, they lead to an interplay of adjustments of energy and momentum, and all of that will actually cause changes in the velocity in the canal or the channel, and the changes in velocity. Again, let's say you had constructed a concrete canal of, let's say, trapezoidal cross section, like so. This is the water level, and this is concrete, so this is fully lined. Now what happens after many years is that you may have vegetations growing. You see all sorts of weeds growing in canals, even though they are lined by concrete. You can have vegetations grow, you can have gravels and deposits being deposited, silt being deposited in the canals. So as they age, as these channels age, their resistance to flow also changes. And sometimes you may have bends and transitions, a wider channel meeting a narrower channel, or vice versa. Their flow may change very slowly over a length of the channel, or it may change very quickly if you have a very large obstruction, or if you have falls. So all of this actually are something called flow transitions. Again, something that we will be discussing in details as part of open channel flow.